Section 5.2.5 concerns an application, compound interest. Now, you may have a compound interest savings account. This may be something that's familiar to you, or you may have a simple interest savings account. In a simple interest investment, interest is paid into your account once per year. In a compound interest investment, interest is paid or compounded into the account multiple times per year. Compound interest is generally a little bit better of an investment than simple interest. To calculate the amount in an account after all of the interest has been added, we're going to use this formula. This formula is an exponential function. We will have a constant base with a variable exponent. Let's talk about what all these variables represent. A represents the amount in the account as measured in dollars, and this is also sometimes known as future value. This is what our investment will grow to attain. P represents principal or amount invested or deposited. This is also in dollars, and this is also known as the present value. So sometimes you may say, I have a certain amount of money that I want to invest now. What's it going to grow to with a certain compound interest savings account in the future? Now, in this formula, we also have R. R represents the rate of interest. And this always must be expressed in decimal form. It's often quoted as a percentage, maybe 3%, something like that. But when we calculate with it in the formula, we have to put it in decimal form, 0.03, for example. T in this formula is time, and specifically, this is measured in years. If you talk about something like 3.5 years, you would plug in 3.5 for T. Or if you talk about a 6-month investment, you would type in 0.5 for T. Now, N in this formula is important. N represents the number of times interest is compounded or paid per year. This is what sets compound interest apart from simple interest. Remember, simple interest is paid once per year. Compound interest is added into your account multiple times per year. So, for example, if the bank says they are going to pay you quarterly interest, that means they're going to pay interest into your account 4 times per year. Or if they say monthly interest, that means you're going to receive interest in your account 12 times per year. A good investment would be daily interest. Now, you have to read the fine print on that one. Some banks use 365, some use what's called the banker's rule and only use 360 days. So you do kind of have to read the fine print if you are checking up on the calculations. So the idea with compound interest, for example, let's suppose that you make an investment that pays monthly interest. You make an initial deposit, let's say you deposit $100 for your principal, and you're going to receive monthly interest. So at the end of the first month, the bank will pay you interest on the initial $100 that you deposited. So that interest is added into your account, increasing the amount in your account. Then the second month, at the end of the second month, the bank will pay you interest again, and this time you will be earning interest not only on the initial $100 that you deposited, but also on the interest that you earned from the first month. This causes your investment to grow exponentially, and over time, it can generate a nice amount in your account. And even though retirement accounts are a little more advanced than what we're looking at here. That's the basic idea. Your money grows very slowly at first, and then over time it grows exponentially. Let's look at using this formula on a couple of examples. Example 5, how much will be in an account in 15 years if the account currently has $1,580.86 and earns interest at a rate of 1.76% compounded monthly, round to the nearest cent. So the first thing that I want to do is identify the formula. A equals P times 1 plus R over N exponent NT. We are looking for the future value. How much is this going to grow to? The principal is the initial deposit or the initial amount in the account. We're going to plug 1580.86 in for P. Then we have 1 plus our rate. The rate of interest is quoted as a percent, 1.76%, but I want to convert that to a decimal, and we do that by moving the decimal 2 places to the left, so we end up with 0.0176. N, if you'll recall, is the number of times interest is compounded per year. We are told that interest is compounded monthly. That means N is 12. Notice the N is up here in the exponent position as well. And we're going to check the balance in this account after 15 years. Now, the good thing about this particular problem is I can plug it into my calculator all in one step. I don't have to calculate any in between steps. So I'm going to type it in just as I have it written. 1580.86, open parentheses, 1 plus 0.0176 divided by 12, close parentheses, type your exponent key, and enter 12 times 15. And the future value then is $2,058, and we're always going to round to 2 decimal places with money to the nearest penny, 0.08. So 2058.08. So if we want to figure out how much of that was interest, we can find the difference between our future value, the $2,058.08, and we can subtract the initial amount, $1,580.86. And the amount of interest that we earned then was $477.22. Now, this is a quite low interest rate. It is reflective of a very basic compound interest savings account that you could open up at a local bank. In order to get a higher interest rate, generally you have to go to a more complicated investment, like an annuity, for example. In an annuity, instead of depositing your money one time and leaving it alone for 15 years, you do as the average person does, and you deposit a little bit at a time over time. For example, you may deposit $50 a month every month into a compound interest account. Then your amount would grow exponentially based on the compound interest and also by your contributions. So that's generally how a retirement account works. Let's try another example. How much should be invested today at an interest rate of 3% compounded quarterly to have $10,000 in 5 years, round to the nearest cent? One thing I want to point out about this one, we're looking at how much should be invested today. This is a one-time lump sum deposit, not where you deposit a little bit over time. Okay, so how much one time should be invested today at a rate of 3% compounded quarterly with a future value of $10,000 in 5 years. We're using the same formula, principal times 1 plus R over N exponent NT. Now, our future value, our goal is 10,000. So in this case, we're going to plug that in for A. What we don't know is how much should be invested today. That's our present value or principal. We do know that the rate of interest is quoted at 3%. As a decimal, that's 0.03. And we are looking at quarterly compounding. That means interest is added 4 times per year, and this is going to occur every year for 5 years. Now, we need to do a little bit of algebra to solve for P. Now, P is being multiplied by this parenthetical element, so to solve for P, I'm going to divide both sides by this number. I'm going to call that exponent 20. Just to make it easy to write down, so that all of that cancels out on the right, and then we can type it into our calculator all in one step. So let's see what we end up with here. We have 10,000 divided by, make sure you get your parentheses, 1 plus 0.03 divided by 4. Don't forget your exponent key. Type in our exponent, and our deposit now should be $8,611. And if we round to the nearest penny, that would be 90 cents. We're going to round 2 decimal places. So 8611.90. So our principal is 8611.90. And then over 5 years, that would grow to $10,000. And remember, interest is free money, right? You make your deposit, you leave it alone, and you benefit from putting that money in the bank. Let's do one more example. What interest rate, rounded to the nearest 1/10%, compounded semi-annually, is required to have $150,000 in 30 years if you have $12,000 to invest today? Now, this is an example of a retirement account that's built on a basic compound interest investment, not an annuity. Let's see how this one turns out. So the question is, what is our interest rate? That's our unknown. So R is what we're looking for here. And we'll remember, round to the nearest 1/10%. Compounded semi-annually, so that means twice per year, is required to have $150,000. That's what we want to retire with. That's our future value. That's going to go over here. And our principal is what we have to invest today. That's $12,000. Remember, R is our unknown. N is 2. Oh, and we've got 30 years up here. We're going to leave it alone for 30 years. So the setup for this investment, we deposit $12,000. We leave it alone for 30 years. And at the end of that 30 years, we come back to extract our money. It will have grown to $150,000. We want to know what interest rate would yield that value. So our unknown is R. We need to solve this equation for R. So I'm going to, first of all, divide both sides by 12,000 so that this coefficient cancels on the right side. Now on the left side, we can cancel factors of 10. I'm going to cancel zeros, and we end up with 150 over 12. The common factor there is 3. 150 divided by 3 is 50, and 12 divided by 3 is 4. Or if you want to just go ahead and turn that into a decimal, you can do that as well. Double check your work. 150,000 divided by 12,000. Let's check our fraction. I don't think we reduced it. It needs to go a little further, 25 over 2. And if we want to figure out the decimal there, that's going to be 12.5. So let's just make it easy and call it 12.5. We have inside parentheses 1 plus r over 2, and let's evaluate our exponent to be 60. Now, in order to solve for r, we're going to have to clear this exponent. This is reminiscent of what we learned in Chapter 1. We can either see this as taking the 60th root of both sides, which is kind of hard to write, or raising both sides to the reciprocal of the rational exponent. That's probably going to be easiest to comprehend. So we have 12.5 raised to the 1/60th power, and notice on the right side when we multiply those powers we get a 1. Next thing we need to do is subtract 1 from both sides. We're working our way into that r. And we have 12.5 raised to the 1/60th minus 1 equals r over 2. The last thing that we need to do here to solve for r is to multiply both sides by 2. That's going to cancel over here, and we will have r at least in decimal form. Let's grab our calculator and evaluate this. And remember, we can do this all in one step. So we have 2 times 12.5 raised to the 1/60th power minus 1. This will be the decimal form of our interest rate, 0.085988. This is a decimal form. In order to quote it, we need to express it as a percent. To go back to a percent, we move the decimal 2 places to the right. And remember, when we're done, we're going to round to the nearest tenth of a percent. So there's my ones place. My tenths are right here in this spot. I'm going to round it to 8.6%. Okay, so at an interest rate of 8.6% compounded twice a year, our $12,000 will grow into a nice little nest egg, $150,000 in 30 years. So that's a great thing to know about exponential functions.